Okay, let's do a couple problems. For hypothesis testing, here's a couple to start off with. We'll call them sigma known problems, and here's why. Let's look at some EMS response times for 40 emergency vehicles. From those 40, we got a sample mean of 13.25 minutes. So forever and always is believed that they perform at a level of wait of 12 minutes or less for any call. So the null hypothesis is less than or equal to 12. If we can take a data set, in this case sample size 40, that has a sample mean of 13.25 minutes, which already is greater than 12, with a standard deviation that's known from the population to be 3.2, if we can take that 13.25 and find that it is significantly greater than 12, we can reject the null. And we can have stated goal be rethought. Here's what we do. We take our information. We know the sample mean was 13.25. Set up our hypotheses. This is an upper tail test because we're trying to see if it's more than 12. We're going to test it at a 5% level. So alpha is 5%, so the probability of making a type 1 error is 5%. 13.25, as we said, was a sample mean. 3.2 was a standard deviation, sample size of 40, and forever and always it's been 12. The z statistic, based on this information right over here, turns out to be 2.471, taking consideration sample mean 13.25, which is greater than 12, divided by the standard error. And again, this is a huge number. Just back of the envelope checking. This is greater than 2. Most likely you're going to reject at a 5% level. This, the probability of creating a z statistic of 2.471 with all this information and this still being true, there's about a 0.0067 chance of that happening, so 0.67% chance. Yeah, that's a little less than 5%. No, it's a lot less than 5%. If you could super reject, you would. But in this case, the p-value is less than alpha, we reject, and we now know that it takes longer than 12 minutes for these folks to get there on average, and we reject the null and say that they have to rethink their stated goal. I've created this template for you to use. I suggest you use it. And again, I'll put this out for you to look at. If you use this over and over again for sigma known problems, this is a z statistic, all you have to do is plug in these 4 values and it spits out value for you. Sample size, sample mean, population standard deviation, hypothesized value. Creates a standard error, the test statistic for you. And since this is an upper tail test, the beak points to the right, is your p-value less than alpha, reject. Now it's not going to automatically update for you yellow which one it would be, upper tail, lower tail. You can intelligently plug that in Excel if you want. I'm just highlighting them here. So upper tail, lower tail probability, the chance of being looking down, you're looking down from that value of 13.25 on the lower 99.33% of all observations. You're pretty far out. Again, the two tail is just a double up. That's the sigma known upper tail test. Here's the sigma known lower tail test with some data. In this case, a person has a can of coffee. A can of coffee says that there's exactly 3 pounds in that can. And that as long as the population mean is at least 3 pounds, so they're saying it's 3, as long as it's at least 3, you as a consumer aren't going to be angry. If it's less than 3, you will. So you want to draw a sample. Here's a sample over here, a whole bunch of cans that were taken, and in fact, it's a total of 36 cans. It's perfect square, helps things along. And you want to test this at a 1% chance of making a type 1 error. So alpha is 1%. So from this value over here, I've run our scripted statistics tool and got a sample mean of 2.92. This should be a mu sigma value of 0.18 here. And we will use the 2.92, compare it to 3, with this as our sigma, and a sample size of 36. And all that information comes down here. In this case, 2.92 is less than 3. Uh-oh. The z statistic really is far down. It's a negative 2.67, so it's greater on an absolute value basis. It's greater than 2, so it puts us out in the uh-oh range and possibly reject. Reality is the probability of you going out and drawing this sample of size 36, getting a sample mean 2.92 with a sigma of 1.18 and the null being true 0.38%, 0.0038. That's less than 1%, so we reject the null, and in this case, goodwill is affected. They are not filling to at least 3%, 3 pounds. Again, here's the model over here, plug in these 4 values, and you're good to go. Same idea. It's a lower tail test because beak points to the left, and we know we're trying to see if it's underfilled. From a two-tail perspective, same idea of filling 30 tubes of toothpaste. The label says 6 ounces. For quality assurance, you want to see if it really is 6. So you want to be assumption that the mean filling weight of for the population is 6 ounces. That's an equal. Notice the previous one, at least, meaning greater than or equal to. First one we just talked about was they have a service time of 12 minutes or less. In this case, it is 6 ounces. And in this case, you drew a sample, 30 of them. Sample means 6.1. The sigma was 0.2. So this is still a sigma node. Alpha is 3%. You want to know if at 3% level of significance, is it filling at exactly 6 ounces? Well, 6.1 is greater than 6, so it's looking into the upper tail. Create a z statistic based on all this information, 2.739. Come over here to the slick little model and put all the information in. 6.1, 6, sample size of 30, and a standard deviation. The two-tailed test gives me a probability of being 0.62%. That is 0.0062. That's less than 3%. Therefore, reject the null, and you find that it isn't filling at that rate of 6 ounces. So here's the thing. In a statistics class, you're more likely to reject a null than you are to not reject a null. That's just because it's easy and the values allow for that. In the real world, we tend to not reject nulls more because things have been forever and always. Just keep that in mind if you're ever in a process on reading things about what's happening around your job or what you're seeing in practice. Boy, you're not rejecting a lot of nulls, and I just rejected 3 in this one. It's because it's very easy to show you how to do it because the data has been created. Okay? How about an unknown case? A speed trap case. We know that the speed limit is 65 miles per hour, so as long as you're driving 65 miles per hour or less, fine. If you're more than 65, you're likely to get a speeding ticket. So you find a location F, and an officer sits there and measures 64 vehicles, and he finds that she finds the average speed is 66.2 miles per hour. Well, from that 66.2, it actually creates a sample standard deviation of 4.2 miles per hour. Here's another template for the t-distribution. I'll save you the effort. 64 is the sample size. You would hope that it's 65 or less. That's what the law states, but you found from the sample size of 64, we're going 66.2, and there's a sample standard deviation of 4.2. Create the standard error, which is the sample standard deviation divided by the sample size. Create the test statistic. Degrees of freedom. All sounds familiar, right? And in this upper tail test, this is the upper tail, beaks pointing to the right. Are people breaking the law? Find that the value is 1.3%. At 5%, 1.3% is less than 5, so therefore you reject this null, and you conclude that, in this case, it would be a good place for a speed trap because people, on average, are proving to go more than 65 miles per hour. I don't know how much more than 65, I just know that it is more in this case. This test. On this same file, I've got a few others for you to look at. Go ahead and take a look. There are additional questions. In this case, we're trying to see whether the mean bonus is different So it's a two-tailed test. In this case, you're using a p-value test, and it's a z-statistic because you're knowing sigma. In this case, you're trying to determine a sample of 75, assuming, can we conclude that an increase occurred? Is it greater than increase over the 14.32? Expand that out a little bit. There you go. And the last one, and again, this will be out for you to take a look at as an example. What we're trying to do is see from this sample, what can we conclude? Well, have cost of a 1 carat diamond. They know it is $5,600. They want to see whether the mean price differs. Is different. That means not low, not high, but possibly both. Is it one or the other? You have to choose. But it isn't a directional test. It's a two-tailed test. So again, more problems for you to practice. These are out here to take a look at. This concludes Chapter 9's problem set. Now forward, we're going to start looking at two sample tests.